So we had worksheet number 7, questions 3 and 4 due for homework last night. We'll do question 4 here as an example. We have 3 charges here in question number 4. We have our first charge up here. We have our second charge, call it charge number 2 down here, and we have a third charge over here. Now the charge of the first one is positive 2.50 times 10 to the negative 2 coulombs. Second one is negative 4.00 times 10 to the negative 2 coulombs. And the third one is positive 3.00 times 10 to the negative 2 coulombs. The distance is given to us 60 millimeters. And the distance between 2 and 3 is 5.00 centimeters. So we got some really crazy units going on in this one, not only because we have to do some conversions with distances, but we have 2 different conversions that we have to do with distances. That first one is in millimeters. We got to remember that a meter is 10 to the minus 3 millimeters, and this one's in centimeters. A meter is 10 to the minus 2 centimeters. So let's do our thing here. Okay, let's draw a free body diagram first of all. We're trying to find the net force on charge 2. We've got to draw that free body diagram on charge 2. Let's pretend number 3 doesn't exist. The force of 1 on 2 is an attractive force. It's attractive because we have opposite charges. Which way is 2 going to be pulled as a result of that force caused by number 1, that attractive force? If 2 is attracted towards number 1, it's going to be pulled which way? It's going to be pulled upwards. Good. So let's say the force of 1 on 2 is going to be upwards. 3 on 2. We got a positive and we got a negative here again. That's going to be an attractive force. If it's an attractive force, which way is 2 going to be pulled? Toward number 3, right? Which is to the right. It's attracted toward number 3. We're going to say that's the force of 3 on 2. Some people get mixed up with this and say, oh, it's got to be pulled to the left because 2 is a bigger charge. That doesn't matter. The force between 2 and 3 is the same regardless of whether you're talking about the force on 2 or the force on 3. It's the same value. It doesn't matter which charge is bigger. That doesn't affect the direction whatsoever. What affects the direction is whether it's attractive or repulsive. 2 is pulled toward number 3. Now, does it move toward number 3? Well, it depends on how heavy it is, right? We don't know anything about that. But we know that it's pulled towards. It feels a force towards number 3. So we got our 2 directions of forces here. Now we got to calculate our magnitudes of forces. F12, we calculated, I believe it was in question 2, to be, was it 2.4972 times 10 to the 9 newtons. Is that right? Big thing with this one again was remembering when we're doing R, KQ1, Q2 over R squared, R wasn't going to be 60. R was going to be 60 times 10 to the minus 3, right? 60 times 10 to the minus 3 meters, or 0.060 meters. When we're calculating the value of F32, we do the same thing, except that the distance here isn't 5, it's 0.05, or 5.0 times 10 to the minus 2. When we calculate that force, it works out to be 4.3152 times 10 to the 9 newtons. Now, if we get a 10 to the 9 newtons, the same exponent in both of these, then in all likelihood, we've done it correct. Right? I mean, if we made the same mistake in both of them, then maybe that could happen. But in all likelihood, we've done this correct if we get numbers like that. Now we've got to redraw this. We've got a force to the right, which has a value of 4.3152 times 10 to the 9. And we've got a force upwards that's 2.4972 times 10 to the 9. We're going to find the resultant vector by drawing the arrow from start to finish. We're going to find that resultant vector by doing the Pythagorean theorem and the angle by doing the inverse tan function. So the magnitude of the force is 4.3 and so on squared plus 2.4 squared. Square root that. We end up getting 4.99, I think it is, times 10 to the 9 newtons. And the angle is going to be found by the inverse tan function. We can always use tangent here, right? Always. Because we're always going to have opposite and adjacent. It's 2.4 over 4.3, and so on. We get an angle there of 30.1 degrees. So 30.1 degrees above the positive x-axis, or 30.1 degrees above the right, or something to that effect. How many people got that question correct? Okay, good. Good. That's your quiz tomorrow, right? That's it. Not the exact same question, but the exact same strategy. I guarantee it won't be any harder than this. I guarantee it won't be any harder than this. The only thing that I might throw in there that wasn't in this question is our coulombs here. There's a pretty good chance that I'll make it something other than coulombs, like microcoulombs or nanocoulombs or something like that, right? Just to throw a wrench in there and see if you spot that. Okay? Good? All right, we also had a little bit of 3 questions, I believe it was, on a little reading that you had on page 537. Any issues with those 3 questions? I think it was fairly straightforward stuff, wasn't it? It's just a matter of, somebody asked me yesterday, is this stuff that we have to know for the test? Why don't you just teach us this for the test instead of making us read about it? The point of this isn't the answers per se to the 3 questions. The point of it is looking through information to find the answers for 3 questions. Because of course we know that's going to happen to us, right? We know that we're going to have to read a page of information and then answer the next 7 questions or whatever it is on our exam. So the point is more to get you good at reading comprehension almost than it is to learn physics from that per se. No issues with it? All right. Yesterday we took a look for the first time at electric fields. We said a field was an influence that surrounded something. A gravitational field was an influence that surrounded mass. What was the direction of the gravitational field? Which way did it point? It always points towards the producer, right? Gravitational field always points toward the producer, and it does because we arbitrarily define the direction of the gravitational field as the way that an object with mass will move if placed in the field. Now, there's a gravitational field right there in front of my finger right now. There's nothing there to feel it. There's nothing there to experience it. But if you were to stand there, or if I was to put my pen there and I dropped it, it would fall downward. That means the gravitational field points downward. It points in the direction that an object with mass would move if placed in the field. What about the electric field? Which way does the electric field point? The influence surrounding a charge. Does anybody remember which way the electric field points when it's surrounding a positive producer, Joel? Away from the positive producer? Well, what happens if we have the other kind of producer, which obviously we can't have with mass because there's only one kind of mass, but with charge we can? What happens if we have a negative producer? The field is always, Matt, going to point which way? Towards it, yeah. It's always going to point towards it. Now, how do we know that? How do we define the direction of the electric field? One way is away from positive and toward negative. But the fundamental way of defining the direction of the electric field is what? The direction that remember, gravity field was the direction that a mass moves when placed in the field. Electric field is the direction that somebody said it? A positive charge moves when placed in the field. So if I was to put a positive charge right here, it's going to move downward in towards it. So therefore, the field is pointing in towards it. If I put a positive charge right here, it's going to point to the right. If it's going to move to the right, which means the electric field is going to point to the right. What if I put a negative in here, right here? Which way is it going to go? Away or towards the producer? That negative is going to go towards it, right? It's oppositely charged to the producer. It's going to move this way. Does that mean the electric field is now pointing inwards? We don't define the direction of the electric field as the way that a negative will move. So a negative moves inward towards the producer in this case. A negative moves outward away from the producer in this case. But the electric field is still defined in the way that a positive would move. So the electric field is opposite to the way that an electron or any kind of negative particle would move. Always remember that. Even if you don't have a diagram of the producer, if you have an electric field, a proton or any kind of positive will experience a force with the field. If you have an electron or any kind of negative, it will always experience a force opposite to the field or against the field. Make sense? Let's draw a couple pictures of electric fields beyond the ones we already have drawn here. Let's combine a positive and a negative. What happens to the field lines in this, around this positive and negative charge when these guys are close enough to interact with each other? What happens to this field line right here? Yeah, it's going to go straight. It just joins up with the next one, right? The field lines are in the same direction, so they're just going to join up. This field line is going to join up with this one. This one is going to join up with this one, and so on. We could keep drawing those like this, right? So on and so on and so on. What if we have two positives? What if we have a positive charge that produces a field away from it, and another positive charge that produces a field that goes away from it as well? What happens to this field line right here when it gets close to this field line right here? Does it join up? No? Brenda, what happens? They repel each other. They push away. So it's going to look something like this. What's the field strength right there? 0. There's no electric field right there. Finally, we had one more diagram. Let's draw this one a little bit different than we drew it yesterday. Two charged parallel metal plates. This time they're vertical instead of horizontal. It doesn't make any difference. The same thought process, same definitions of direction apply here. Let's make this one negative and this one a positive plate. What's the direction of the electric field inside or between these two plates? Left, right, up, down, into the page, out of the page? Do you know? It's pointing to the left, right? Now, what's the big difference between this electric field that I'm drawing right now and this electric field and this one and this one? What's the big difference with this electric field? Good. It's a uniform electric field. No matter where you are, the strength of the electric field is the same. Unlike this one, the strength of the electric field is stronger where the field lines are closer together and weaker where the field lines are further apart. When the field lines are parallel, it's a uniform electric field. The field here and here and here and here and here and here are exactly the same values. Yes, yes, only in between the two. Now, even if you look at the edges, you saw yesterday that there's what we call these edge effects. The field lines curve at the edges, and we don't worry too much about that. But in the end, at those edges, just outside of these two parallel plates, the electric field wouldn't be a uniform field because these field lines aren't parallel to each other. Hey, I got a quick question for you. If I was to put a negative charge right there, where would it go? Ashton? Go towards it like this? Almost, but not quite. Yeah. It would follow the field line, but it would go opposite to the direction of the field line, but it would follow that field line. Does that make sense? If I put a positive right here, where's it going to go? It's going to go out, right? But it's not going to go straight out. It's going to go along the field line. The charges follow the field lines, either with the field line or against the field line. 3 equations that we saw yesterday, 3 new ones, 2 new ones, I should say. The Coulomb's law one we had already done quite a bit of before yesterday. The first new one was this one, E is equal to KQ over R squared. The second new one was this one, E is equal to F over Q. Both for electric fields. First one, the electric field around a producer. The second one, the electric field experienced by something, experienced by an experiencer. What does this Q stand for right here? Tom, what does that Q stand for right there? The charge of the producer, right. It's the charge of the producer. There's two charges that we can be dealing with here, right? Whatever's causing the field and whatever's experiencing the field. This Q stands for the charge of the producer. What does this Q stand for? Brianna, what's this one stand for? What's the bottom one? Good, the charge of the experiencer. What does F stand for? Nick, what does F stand for there? Yeah, the force felt or the force experienced by the experiencer. All right? You had a couple questions for homework on this stuff as well. It was on page 548. Any issues with those questions on page 548? The key to these really is just recognizing what's the producer, what's the experiencer, and what you have more information about. The equations are both pretty easy. They really are, as long as you know which equation you're supposed to use. And even that's not hard, as long as you recognize this is the producer and this is the experiencer. The producer is the one that I have more information about, or the experiencer is the one that I have more information about. These are both okay? All right, let's take a look at another one here, 11.2 on 549. This one says, determine the electric field at position P that is 2.2 times 10 to the negative 2 meters away from the center of a negative point charge, 1.7 times 10 to the minus 6 coulombs. It's a negative charge. That's important because that's going to not help us with the equation, but it is going to help us with the direction of the electric field. Let's draw it. Here's a negative point charge, and it's got an electric field surrounding it like this. It points towards it. And we're trying to find the field strength out here, which is 2.2 times 10 to the negative 2 meters away from it. The charge of this thing right here is going to be 1.70 times 10 to the negative 6 coulombs. Tell me, is this a producer or experiencer? Is it causing the field out here at this point X? Or is it experiencing the field out there at that point X? Somebody said it. I think somebody said it. Oh, maybe not then. It's a producer, isn't it? And it's causing the field out there. Here's the rule of thumb. If you're trying to find the field strength, a certain distance from the charge, well then probably what you have is information about the producer. If you're trying to find the field strength where the charge is, then probably what you have is information about the experiencer. Here we're trying to find the field strength a certain distance away from the charge. So that charge is going to be a producer. That means we're going to use our producer equation. E is equal to kq over r squared. Now, in the event that you were given information about both the producer and the experiencer, you got to be careful. You're allowed to use either equation as long as you use the proper givens for it, but you got to be really careful with the Q. Okay, what a lot of times people will do is say, if you got the charge out here, say, they'll plug in the wrong value of charge right here. They'll mix up the producer and the experiencer. Okay, if you're using the producer equation, that's fine. Go with it. Use the producer charge. If you're going with the experiencer equation, that's fine. Use the experiencer charge. All right, so we got 8.99 times 10 to the 9 times Q, which is 1.70 times 10 to the minus 6. Should I have put the negative in there? Negative 1.7? Just like with Coulomb's law, we always drop the sign of the charge. Always. Anytime we plug it into an equation, we always drop it. What do you think the most common mistake with this problem is going to be? Forgetting to square the r. It happens all the time. Let's do this one as a class here, just to show you a little bit of a little thing with the bottom here and how you can do that in one step. 8.99 times 10 to the 9 times 1.7 times 10 to the minus 6. Let's press equals, and then let's divide by the denominator. But if you're going to square the denominator all kind of in one step, then let's use some brackets. let's go 2.2 times 10 to the minus 2, end bracket, and then let's put the square outside the brackets. When we do that, we get an answer of 3.15 times 10 to the something. Yesterday I saw somebody counting up, moving the decimal place over. I'll show you another little trick here. If you don't like doing that, if you don't like moving the decimal place over, do this. Go mode, scientific, and then just times that by 1. Because you're going to end up with the same answer, right, if you times it by 1. But now that we've put it in scientific notation, kind of does it for us, right? 3.16 times 10 to the 7. 3.16 times 10 to the 7. What would the units be for this? What did we say the units were for electric field yesterday? They're still the same. Just because we're using a different equation doesn't change anything. 3.16 times 10 to the 7 newtons per coulomb. The direction is towards the producer. Right, left, we can't say that because we don't know where the experiencer is or where the point is, which direction, but we know that it's toward the producer. I think you'd agree that this is not too hard of a problem, right? And generally they're not that hard of a problem, again, as long as we recognize what we've got, whether we've got a producer or an experiencer. Then it tends not to be very, very hard. Yeah, both of you can go. All right, try these ones. All right, let's take a look at question number 2. Just a quick thought with question number 1, though, before we move on to question number 2. The equation E is equal to KQ over R squared doesn't give us the direction of the field here, so we have to find some other way of getting the direction. We're asked to find what the sorry, not the direction, but the sign of the charge here. We're asked to find the value of the sign of the value of the charge and the sign of the charge, but we're not going to get that from the equation. So what are we going to do? Well, we're going to draw a picture. We've got a charge here, and there's an electric field surrounding the charge that is directed away from the charge. What kind of charge must that be if the field points away from it? It's got to be positive, right? Simply based on the definition of the direction of the electric field. We don't need to do any equations to figure out that it's a positive charge. We need to use an equation to figure out what the value of that charge is. And that's going to be our producer equation, KQ over R squared. Number 2. An electron has a charge of 1.6 times 10 to the minus 19 coulombs. At what distance from the electron would the magnitude of the field be that value? Here's my electron. The field strength over here, a certain distance r away from the electron, is 5.14 times 10 to the 11 newtons per coulomb. If I have information about the electron, the charge of the electron is negative 1.60 times 10 to the minus 19 coulombs. Tell me, is that electron a producer or an experiencer? It's got to be a producer. How do you tell that? This is kind of tricky in terms of the wording, whether you got a producer or an experiencer. How do you know whether you have a producer or experiencer in this question? Here's a rule of thumb, right? We talked about this a little bit before you did these questions. If you're trying to find the field strength somewhere other than where the charge is, it's got to be a producer. Look, the field strength right here is 5.14 times 10 to the 11. Okay, that's great. This electron is not experiencing that. But if the electron's not there, then the electron can't be experiencing that. If it's not experiencing that, then it's got to be doing what? It's got to be producing it. So we kind of look at it as, oh, it's not an experiencer because it's not in the right place to experience that field. So it's got to be a producer. Now, could it potentially experience a field due to something else? Maybe. We don't know anything about that because we're not given any other information. Maybe it could be an experiencer for something else, but it's not in this question. The field that we have right there, 5.14, has got to be the field caused by the electron as opposed to experienced by the electron because it's not in the same place as the electron. So it's a producer. We're going to use the equation KQ over R squared, and then we're going to rearrange that and solve for R. The R squared goes up by multiplying. and then the E is going to go down by dividing. How am I going to get rid of that square? What do you do to get rid of a square on the left side? Square root it. So if we square root r squared, we get r. If we square root this, we get that. I think when we do the math there, we end up getting 5.29 times 10 to the minus 11 meters. Joel? Yes? Does that make sense? All right, what about this one? Oh, what do we have here? We're trying to find the field strength here somewhere other than where the charge is, so that must mean we're dealing with what? Producer, experiencer. You look like you're ready to tell me there, Nick. You're dealing with a producer, because if you're dealing with an experiencer, you'd be trying to find the field strength where the experiencer is. We're not here. The trick to this one is that there's two of them. There's two producers. We want to find the field strength at point P due to A and B. Now, the first thing that we're going to do here, this is not unlike some of our Coulomb's law problems, but it's not exactly the same thing either. It's a little bit different. Similar, but not exactly the same thing. First thing we're going to do is draw a diagram. It's not a free body diagram, because free body diagrams show forces. We're going to draw a diagram showing the field. The field caused by A, the field caused by B. Which way does it point? Well, let's pretend B doesn't exist. B's not there. We're trying to find the field strength, or the field direction, to the right of a positive producer. Which way does the field point around a positive producer? Points away from it, right? Well, the only one I care about is this one, right? The field at point P points to the right as a result of charge A. So we're going to say EA, the electric field caused by A, is to the right. Now let's pretend A isn't there. B is a positive producer as well. The electric field caused by B is going to go out, away from it. There's only one of those fields I care about, and that's the one that's to the left of the positive producer. It's going to be pointing towards the left. The field caused by B is to the left. Now I've got the direction of both of those fields. Let's calculate the value of both of those fields. Once we get that, what do you think we're going to do with them? Once we get EA and EB, we're going to add them up, right? We got to be careful, though, because one of them is going to be positive, one of them is going to be negative. The whole reason we drew the diagram, though, was to help us to remember when we go to add them up that the EB is going to be a negative value. All right, let's get both of those field strengths here. Let's say EA is going to be KQ over R squared. It's a producer, so let's use the producer equation. Make sure you use the right charge here. It's 1.50 times 10 to the minus 6. Even if it was a negative charge, we'd still make it a positive. R is what? 3.3 times 10 to the negative 2? Pardon me? 3.3 times 10 to the negative 2, is that right? Just because you're given a number for a distance doesn't mean it's the number that you're going to plug in. Why is the value for R not 3.3 times 10 to the negative 2? Jordan? Yeah, it's midway between A and B. Now, somebody asked me the other day, I can't remember if it was this class or another class, why don't you divide R by 2? Why don't you divide the distance by 2 to get the radius? We're not talking about a circle here. This has nothing to do with radius and diameter. R stands for a distance from something to something else. We're not dividing this by 2 because it's radius instead of diameter. We're dividing it by 2 because we don't have the distance from point A to point P. We've got to divide it by 2 to get that distance. So it's going to work out to be 1.65 times 10 to the minus 2. And then, of course, we can't forget to square that. The most common mistake that people make here, forgetting to square that. Does anybody have that value? Yeah, it is. Do you have the answer? Let's try that again then. Is there a way that I can edit that? Second enter. Oh, look at that. Learned something new. Thank you, Jack. So 8.99 times 10 to the 9 times 1.5 times 10 to the minus 6. Now let's divide that by 1.65 times 10 to the minus 2. And let's square that. We get 4.953 times 10 to the 7. And the units for that would be newtons per coulomb. Let's get the value of EB, the electric field caused by B here. Again, let's make sure we use the right charge. The distance is going to be the same, not because it's the same place, but it's going to be, since it's midway in between, it's going to be the same distance from B as it is from point A. What do we get for the electric field there? Jack, is there a way that I can go back and edit this one now? No? Press what twice? Oh, wow. Wow. This is great, Jack. You know what? I'm going to show that. I'm going to slip that into my next class, and I'm going to take complete credit for that. I'm just going to look so smart that I know everything about this calculator. What is it? 1.5. We're going to 2.0 now, right? Now let's divide that by, once again, 1.65 times 10 to the minus 2. We get 6.604 times 10 to the 7. Now let's add them up. The net electric field is EA, which is a positive value, 4.953 times 10 to the 7, plus the negative value of EB, 6.604 times 10 to the 7 newtons per coulomb. And we do that, we end up getting negative 1.65 times 10 to the 7, which means it's going to be to the left. So similar to what we were doing here a couple of days ago with electric forces, 3 charges, right? Trying to find the force on the middle one due to the other 2, but not the same. A, because we're dealing with fields, not forces. B, because we've only got 2 charges, but we still treat it in a similar way here. Give you a chance to write that down if you haven't already. All right. That's not what I wanted you to see. That's not the one that I wanted to show you. There it is. There we are. Page 550. Must have pressed it twice. Page 550. Let's do these practice problems, please. So in addition to these questions on 550 that I want you to complete for homework, if you haven't finished already, I want you to make sure that you have your check and reflect questions on page 553, number 1 to 9 done. So your homework, page 550, 1 and 2, page 553, 1 to 9. That's it.